Hey everybody, welcome back to another lecture video. This time we're looking at chapter 9. We're going to be talking about electrons in atoms and the periodic table. So to start our topic, let's talk about what happened on May 6th, 1937. So while landing in New Jersey on its first transatlantic crossing, the Hindenburg, which was a hydrogen gas-filled blimp, burst into flames, destroyed the airship, killing 36 of the 97 passengers that were aboard the ship. Apparently, the Hindenburg was landing, and leaking hydrogen gas got ignited. So it was landing, there was some leaking hydrogen gas, it ignited, the ship exploded, and it destroyed the airship. Now, the skin of the Hindenburg, which was constructed of a flammable material, might have also been partially to blame for the demise, right? It completely caught on fire and went up in flames. Now, the Hindenburg was filled with hydrogen, a reactive flammable gas. Now, what makes hydrogen reactive? Or why is hydrogen gas reactive? And that's one of the questions that we can attempt to answer in this chapter. Now, modern blimps are filled with helium. It's an inert gas. Inert means non-reactive. Helium gas. The nucleus of a helium atom has two protons. So the neutral helium atom only has two electrons. It's a very highly stable configuration. And in this chapter, we're going to learn about the models that explain the inertness of helium and the reactivity of other elements. So what is it about helium gas that makes helium inert? What makes hydrogen so reactive? Elemental hydrogen exists as a diatomic element. Hydrogen atoms are so reactive that they react with each other to form a hydrogen molecule, where helium exists as a monoatomic element. So what is it about hydrogen that makes them so reactive? And are other elements as reactive as hydrogen? The reactivity exhibited by hydrogen is actually seen in other group 1 elements, such as lithium and sodium. And that has to do with the fact that they form the same kind of ions. They are all in the same column of the periodic table, and as such, they are going to have some similar properties. The inertness of helium is also seen in the inertness of neon and argon and xenon and krypton, the other noble gases. I don't remember what order they're in off the top of my head. Helium, neon, argon, krypton, xenon, radon. So I stuck krypton. I missed krypton. And then after potassium, we go rubidium, cesium, francium. Okay. Not that that's important. So Mendeleev's periodic law actually sums up these observations. When elements are arranged in order of increasing atomic number, certain sets of properties actually recur periodically. And there are some models and theories that will help us explain the observed behavior of the groups of elements, such as the group 1 metals and the noble gases. Group 1 nobles. Okay. Now, to examine these questions a little deeper, we need to examine two important models, the Bohr model and the quantum mechanical model, that propose explanations for how the inertness of helium and the reactivity of hydrogen, and explanations about the periodic law. Now, these models explain how electrons exist in atoms and how these electrons affect the chemical and physical properties of the elements. And the two sort of main scientists that played a role in developing the quantum mechanics or in these theories, I should say, are Niels Bohr and Erwin Schrödinger. Now, these guys, along with Albert Einstein, played a role in the development of the theory of quantum mechanics, and even as they were doing it, they were bewildered by their own theory of the wave-particle duality for the electron. Wave-particle duality. So while they were figuring these things out, they were still wrapping their minds around what their experiments have revealed to them about the nature of electrons, which is that they had wave properties and particle properties, which is something really, really weird to think about. And so we need to talk a little bit about waves so that we can understand what wave properties they saw. Now, when we talk about light, we're going to be talking about waves. Light is a wave. And we're going to use some analogies. We'll talk about sound waves. We'll talk about vibrations. These are also waves. And then we'll try to relate that to the electron's wave. Now, the particle nature of matter is one that you would already know. Play pool or billiards, right? And you know all about the particle nature of reality. You knock a ball into another ball, and that will transfer its energy and send the ball that you struck reeling off into another part of the table. So when molecules interact like that, we say that they have particle nature. So if a electron is flying in and it strikes, a proton, let's say, or strikes some material, let's say the atoms on these material, and they collide, and this sends a different electron flying off into space in a different direction. That would be the particle nature of electrons. They would interact with each other on a one-to-one basis, the same way that molecules of gases bounce off each other or that billiard balls bounce off each other. So wave and particle are not the same thing at all, yet it looks like electrons are maybe made up of a little bit of both, or they are both at the same time. Very, very strange stuff. This is what leads to some people referring to quantum mechanics as more of a statistical theory as opposed to a determinant theory, where we can actually say A equals B. Instead, we say A can equal, all of these different types of B. It's a little bit of a different type of theory. So let's get into it. The interaction of light with atoms actually helped shape scientists' model of the atom, and so it's important that we understand how light behaves. Again, light is going to be a key way that we probe things. In fact, light microscopes, right? We use light to get down to the small and see things that are smaller. Light does have a limit, but for the most part, light does interact with atoms and really determines the colors that we see in the molecules and the shapes and all of that we're able to visualize. Light is a form of electromagnetic radiation. We call it electromagnetic radiation, or EM radiation for short, because it's made up of two parts. It has an electro component and it has a magnetic component. I don't know if I have a good image of these two components working side by side. In fact, I most likely don't. So if we could imagine that this wave that I'm showing down here has an electrical component in red, meaning it's got a negative electrical component, then it's positive, and then it's negative, and then it's positive, and then it's negative, and then it's positive. We would say that this light wave is oscillating or going back and forth between these two extremes, the negative and the positive, negative and the positive. And this would be true for the electronic component of this light beam. Now, there's also a magnetic component that travels perpendicular to that. So if you can kind of imagine this dotted line coming in and out at you. So I'm going to make it really dark here and say this is coming out at us, and then it's going back into the the distance, and then it's coming out at us here, and then going back into the distance here, and then coming out at us here. Can you imagine that? Like if there was two waves, one wave coming out, one wave going back, one wave coming out, but right at us and away from us, because it's perpendicular, meaning they're 90-degree separation. One wave would be traveling up and down, the other wave traveling side to side, and there's 90 degrees separating those two planes. So the magnetic portion is also oscillating between a positive and a negative, and this is where the electromagnetic comes from. Some side effects of this: when we move charges, so like if electrons are moving through a wire, that generates a magnetic field. If we are moving magnets around wires, that generates an electric field. Light itself can interact with molecules that have little dipoles to them, little magnetized or polarized bits to them. And so there is interaction between light and or electronics and magnetism. They are two sides of the same coin. We make electricity by moving magnets through wires. We use waterfalls and dams and things that move water, hydroelectric generated, or if they're nuclear generated or just coal generated. We use heat, we burn things to boil water, and then water turns into steam, and the steam turns a turbine which is loaded up with magnets, and those magnets pass over wires and generate electricity. Any kind of generator works that way, and any kind of motor works the opposite way, where you would sometimes you would use, like an electric motor uses electricity to actually spin a magnet or to spin a turbine that has magnets on it, to make wheels turn or to make a lever go up and down. And so any kind of machinery that uses electricity usually involves some kind of magnet if it's got moving parts. Okay, that's enough about that. So light is electromagnetic radiation. It's generally just the broad category for electromagnetic radiation. We're going to divide that into some more specific types like microwave, ultraviolet, visible. But for now, we can just say light. Light has a speed. It travels at 186,000 miles per second, which means it can wrap around the Earth several times in a second. Our Earth is only 24,000 miles across or around at its equator, assuming you all subscribe to the round Earth theory. I don't mean to call it a theory, it's a fact. And light also has properties of both waves and particles. And so we're going to look at how light works as a wave, and then I will show you how light works as a particle. Now, in our SI units, this would be 3.0 times 10 to the 8 meters per second. Side note, we can actually use these to calculate the speed of something. So let me give you an example. Let's say that I want to know how long it takes, how many seconds does it take for light to travel some distance, any distance. We can make up whatever distance we want. We could say, how long does it take light to travel, 11 feet? Let's do that. How many seconds for light to travel 11 feet? Now, of course, you could do this for 8 miles or for, whatever you wanted in any unit. Now, I want to use the, we could use the miles per second or the meters. I like the meters per second. We can do a quick conversion. So 3.0 times 10 to the 8 meters per second is the speed, which, if you notice, is a conversion factor between distance and time. So since we want to know time, we need to start with distance. So we have 11 feet, but that's not in meters. So I'm going to say in 1 foot, there's 12 inches, and in 1 inch, there's 2.54 centimeters, because every 100 centimeters is 1 meter. So that'll get me into the proper units of meters, and you can see that if I cancel my units. So now I'm in meters. Last thing I want to do is figure out the time. So it looks like it's 3.0 times 10 to the 8 meters in every second. So now that meters is also gone, we can just do the math here. Now I encourage you to give this one a shot. It's got scientific notation in it on the bottom of a fraction, so that's usually going to present some trouble. 11 times 12 times 2.54, all divided by 100, all divided by 3.0 times 10 to the 8. All right, so I'm going to give you my answer in scientific notation. I get 1.1, let's say 1.12 times 10 to the minus 8 seconds. So, yeah, that didn't take very long. We probably could have picked something more like, how long does it take light to travel 670,000 miles or something like that, distance to the Jupiter or something like that. We could have picked some other distance. That's not the distance to Jupiter at all. But you know what I mean. We could have picked something. If we knew the distance to the moon, we could actually confirm that it takes a little under 2 seconds for light to travel to the moon. That would actually have been a much better problem to do. Yeah, I wish I knew the distance. Here, actually, do I have my phone on me? Let's see. I don't think Siri's listening. What's the distance to the moon?
Here's what I found.
Distance to the moon. Yeah, no. It's not going to tell me. Here we go. The distance is... Yikes. That's a giant number. 400,000 kilometers away. 400,000 kilometers. A kilometer is 1,000 meters, so let's just say it's 400 million meters away. Given that, 3.0 times 10 to the 8 meters per second. When we sent missions to the moon, one of the things they did was leave a reflective plate on the moon that we could then use to bounce lasers off to periodically measure, well, not periodically, they wanted to measure the exact distance to the moon, and they used light to do it. They bounced a laser off the moon, and they recorded how long it took for the laser to leave and come back. And since light travels at a constant speed, that's where they can get roughly the distance from. So let's kind of do a reverse calculation. Let's do 400 million meters divided by 3 times 10 to the 8 meters, and it comes out to be 1.3 seconds. So a little under 2 seconds, probably a lot under 2 seconds, depending on your idea of a little or a lot. But under 3 seconds is what it took for the light to get there and back. So yeah, that's just another version of this type of problem. Okay, sidetracked. So light has wave and particle properties, and you can see what a wave property is. This is droplets of water, right, dropping into some more water. And the waving is actually the height of the water, right? It's going from slightly high to lower to slightly higher to lower. You've all seen this before. Now, this is what waves do. They alternate between two extremes, high and low in terms of the water height or waves at the ocean, but alternating between negative and positive in terms of the electric component of light, and so on. All right, so when the water surface is disturbed, waves are created, they radiate outward, and the wave carries away the energy as it moves through the water. Most waves that we talk about are going to be in 3D space, so usually they're spherical and they radiate outward, like a explosion in a movie, right, goes outward and upward. That's kind of how waves, to make our picture of the electron wave more complicated, they're 3D and three-dimensional and not flat waves like these are. But you guys would know a little bit about water waves. Now, let's talk about how we quantify some of the properties of a wave. We talk about the wavelength. The wavelength is the distance from peak to peak, or crest, trough to trough. Peaks to crests, those are the same thing. Crest to crest, that's the wavelength, and it's usually given in meters, and it's used the Greek symbol lambda. Yeah. So when light is produced by like the sun or by a light bulb, it contains all the spectrum of wavelengths of light. Therefore, all the spectrums of color, and we can separate these out using a prism to see the light as their different colors. Now, a white light source, like I mentioned, can come from anything that's burning or glowing because it's hot. Temperature is a factor in this. So as objects start to get hotter, they start to emit different types of light. First, they start to emit radio types of light, radio wave light that we can't hear and we can't see and we can't feel. Then there's microwave type light. As the energy gets hotter and hotter, more and more energy, microwave light comes out. After that, we get infrared light. This is what our body has sensors in it all over our skin to detect. We can detect this as heat or warmth. And so we're able to detect infrared light when it's shining on us. But infrared light is what warmth is, and that's what comes from the sun. It comes from a fire. It comes from anything that's hot. So if you had, a hot piece of metal and it's cool enough to touch, but you put it in your pocket, it's going to generate some warmth in your pocket. You're going to feel warm from that because it's emitting those warm infrared rays. Beyond that, when you start to get into something that's even hotter than just feeling hot, it starts to glow and it starts to give off the rainbow color, starting with red, working up to violet. This is why things that are only a little bit really hot are glowing red, and when they're really hot, they're glowing blue or glowing white. Have you ever seen something glowing blue or glowing white? Well, look at the sun. The sun is white hot. And that's because all the colors of light add up to make white light. Now, our eyes do limit us in the amount of light that we can actually detect. We're unable to detect really anything other than red, blue, and green. And so things that we see are really just a big lie. Our eyes lie to us, our brain lies to us. But that's how we've evolved, and that's how we have to deal with the world. So our eyes are not the best judges of color. Everybody probably experiences color differently, yet we've all agreed on those colors and what we call them. So let's say you're looking at something that's red, and your friend's looking at it also. It might look darker to you than it does to your friend. Now, you would never know that because you both look at that same color and you both look at each other and say that's red, and you both agree that when you're looking at that color and when they're looking at that color, that you're both going to call it red, even though to you it may look darker than it does to them. And this has to do with the cones and the rods in your eyes and your ability to detect certain colors. But anyways, we see colors: red, orange, yellow, green, blue, indigo, and violet. And we can see these colors when they're passed through prisms, or when they're refracted by water droplets in the air after a rainstorm, or by other things that like oils and liquids can often give us these types of rainbows. Red light with a nanometer with a wavelength of 750 nanometers, and down to about violet light of 400 nanometers is about the range of what we can see with our eyes. The shortest wavelength of visible light, again, is about 400 nanometers. Now, 1 nanometer is 10 to the minus 9 meters, or 1 times 10 to the minus 9 meters, and it is very, very small. The presence of white light, is actually what's responsible for us being able to see colors in everyday vision. If we didn't have white light, then all of the color options wouldn't be there for us to selectively see. Now, what I mean by selectively see is that when all of these different colors of light shine down on us, only some of them actually make it back to our eyes. A red shirt appears red because it reflects red light. The shirt absorbs all of the other colors of the light except red. So even though white light full of all the colors is hitting it, some light stays in the shirt and other light bounces off the shirt. So my favorite question to ask when I'm teaching my biochem class is, what is a plant's favorite color? What color do all plants and trees and grass, what's their favorite color? Well, it's not green. In fact, green is the garbage color that not a single plant seems to want. There are some purple plants out there that clearly like green and don't like purple. But it's not about, so it's just, you got to train your mind to now think critically. Yeah, they're green, but they're green because that's the color that bounces off of the plant. So green light is not going to make your plants grow, right? If you ever got a seed when you were little and thought a green light bulb would help it, that's the worst kind of light you could ever give a plant, because it's the light that literally every plant is just sending back out into everyone else. So on top of that, our eyes lie to us too. So you're looking at some colors here. No doubt you can see this little section of yellow right here. There's not a single drop of yellow light coming off of your device. No device that you're looking at to see this yellow is producing anything near yellow light. All of our devices are built on something called a pixel, and a pixel is made up of 3 colors. It's got red light, green light, and blue light in it. And these are basically made up from the same, this is kind of mirroring how our eyes work. Our eyes only have 3 color detectors. They have red, blue, and green color detector. So we have cones that can detect the red region of light, the green region of light, and the blue region of light. And let's say if there was actual yellow light shining on you, if you had a lemon, let's say you're holding a lemon in front of you and you're looking at it, well, light bouncing off that lemon is going to be yellow, and it's going to trigger a little bit of your red area and a little bit of your blue area, just the way that real yellow light would have triggered a little bit of your red and a little bit of your blue. The real yellow light you don't have a receptor for, but yellow light is close to red, and so it would give you a little bit of red and it would give you a little bit of blue, and that's what your brain has memorized is yellow. I can't spell. Yellow. So now I want to trick you and show you yellow light, so all I have to do is give you a little bit of red and a little bit of blue, the same way that real yellow light would have done to your eyes. And guess what? Your brain thinks it's seeing yellow. Yeah. So that's how it works. So one of the funny things about color is that your brain actually even makes up colors. So you have a color in your mind that you think, of purple. Okay. Now I just told you that violet is a color, but we can't really see violet very well. We can see blue. Violet isn't a color, but what we think of violet is a mixture between red and blue, right? And here's what happens: our brains, they see violet light. Now, violet light triggers some of our red and triggers some of our blue receptor. So your brain goes, oh yeah, I know when that I see that all the time. All the time, whenever something triggers a little bit of red and a little bit of blue, it's called green. And that's usually the case, because when you see green light, it's centered right in the middle of the other two cones. And so we detect the green light from a real green source, and it lights up a little bit of our red and blues at the same time. But now, when we see purple, we see red light up, we see blue light up, but the brain's going, hey, wait a minute, where's the green? There's no green. It's something your brain doesn't understand. And so it has to assign something. We see something when this happens, and we see purple. So the purple light that we see is a brain thing. It's not a real thing. And I know that's weird, but think about it for a second. Everything in the world is only real to you. You know, you could talk about the water floating around, in the coast of somewhere, but until you actually see it and touch it, your brain, it doesn't know it's real. And everything that you experience has to be interpreted by your brain. So even though I'm seeing something with my eyes, there are people that have genetic, or brain defects in their vision centers where their brain tells them they're seeing something even though their eyes are literally not connecting any light or getting any light. So there's miscommunications that can happen in our brains. That's where reality happens, is in our brain. So someone who sees things that aren't there, those things are still real to that person even though they're not real to us. And so we all see collectively a color called purple that doesn't really exist in nature, but that we, our brain has to make sense of. Now, that being said, I'm talking about purple light. I'm not talking about purple objects. Purple objects, again, that is a play. There's a difference between colors that are like paint colors and light colors. All paint colors add together to make black. All light colors add together to make white. So we can't think of them the same way. So don't let what you know about paint colors confuse what I'm trying to tell you about light colors, okay? We know less about light colors than paint colors. We grow up touching things, we don't get to touch light. So this is going to be slightly different than what you imagine. So again, molecules, atoms, these are going to be the reason why some shirts absorb colors and reflect red, while other shirts absorb different colors and maybe reflect blue, okay? And that should already get your brain thinking how neat and crazy the world is, because everything's a different color. That just means the way it interacts with light is also really different. Let's talk about the different things, different ways that we can talk about light as well. In addition to wavelength, we can talk about its energy level and we can talk about its frequency. Frequency is got the designation nu, N-U, that we get from Greek. And this is not V for velocity, this is frequency nu. And this is defined as the number of cycles or crests that can pass through a stationary point in 1 second. So we would imagine that as light is traveling in this direction, if we had a piece of tape or something and we were trying to see how many crests pass by this piece of tape in 1 second, and we kept track of that, that's what frequency is. And so another example is if you've got a grandfather clock, or if you know anybody that has a grandfather clock, every time this clock goes back and forth, right, all the way this way and all the way this way. That's what 1 second is. And so if you can think about this point as being the stationary point, this pendulum on a grandfather clock actually has a frequency equal to 2 because it passes one crest and then another crest. One direction and back again. 2 crests of this wave pass, and any oscillation is a wave. Any oscillation between 2 points. We always show waves like this, but this guy's waving. He's waving from here to here, back and forth, and it takes 2 seconds for him to go. Oh, 1 second for him to go. Wait, click, click. That's 1 second. That's 2 seconds. So, wait a minute. So yeah, okay, sorry. 1 full wave, crest to crest, is 1 full cycle. 1 full cycle. So he starts here and he ends here. That takes 2 seconds. For light, the frequency is a much higher number. For frequency, we can actually figure out the frequency by kind of an inverse of the wavelength. They're inversely related. So the bigger the wavelength, the smaller the frequency, and the smaller the wavelength, the bigger the frequency. That should make sense. If I have a wave like this and a wave like this, you can see that this wave on bottom that has a much smaller lambda, a much smaller wavelength, in 1 second, since all light travels the same speed, I'm going to get lots of crests passing through this point compared to a bigger wavelength, a bigger lambda, for the same speed. So frequency goes up when wavelength goes down. The same is true of energy. Imagine that you are sticking your finger in a pond trying to make ripples. If you stick your finger slowly, you get ripples that are spaced out, right? If you do it fast, you get closely spaced ripples. Well, that's the same thing as frequency. To get frequency higher, you need more energy. You need to dip your finger in there really, really fast, over and over and over. So look at this, this diagram then. So on this side, we've got high energy, which means that we have low wavelength, right? Short distances, and we have high frequency. And on the other side, where we have low energy, we have high wavelengths, really big wavelengths, and that gives us low frequencies. So light. Light can be viewed as a stream of particles. Think about a river. A river isn't just a big blob of water, right? It's actually a bunch of little tiny water molecules that are all holding on to each other, moving in the same direction. So the light river that we see in a flashlight or coming from the sun, those little parts of light are called photons. And a little photon of light carries with it some energy. Now, the amount of energy carried by this little photon of light depends on the wavelength. The shorter the wavelength, the greater the energy. Light carries more energy if the crests are shorter together. And so if we were to compare, red light and violet light has the shorter wavelength. It has more energy in it per photon than red light, which carries a longer wavelength. Okay, so to summarize, before we get to the types of light, electromagnetic radiation is a form of energy that travels through space at a constant speed of 3×10⁸ meters per second. It can have wave-like or particle-like properties, and we haven't looked at those particle-like properties yet. The wavelength of the electromagnetic radiation determines the amount of energy that is carried by one of its photons. Shorter wavelength, more energy. The frequency and energy of the electromagnetic radiation are inversely related to wavelength. So as energy is down and frequency are down, wavelength is up. And as wavelength is down, frequency and energy are up. So frequency and energy go together. They're opposites of wavelength. The entire electromagnetic spectrum with short wavelength and high frequency radiation on the right and long wavelength and low frequency radiation on the left is shown. And you can see visible light is the small little sliver right here in the middle. If this was really how wide the scale was from one side to the other, then the actual line of visible light would be so skinny that I actually wouldn't be able to draw it on here, because any line we draw misrepresents that as being a bigger proportion of light for visible than exists. There is much more light in the world that exists that is not the kind of light that we can see. The kind of light that we can see is actually so tiny compared to all the light that's out there. So the shortest wavelength and most energetic is the gamma ray. Gamma rays, you can see the range here. These are produced by the sun, by stars, certain unstable atomic nuclei on Earth. Excessive human exposure to gamma rays is actually dangerous because of the high energy that gamma ray photons emit, and they can actually damage biological molecules. I think I'm going backwards on here, so let's see. Am I going backwards? Yeah, I'm going backwards. So I'm not here yet. Let's leave this picture up. So I'm going from right to left, but I think my pictures are going from left to right. So maybe let's go from left to right. Okay, so let's start with the radio waves. So the longest wavelengths of light are radio waves. These are used to transmit signals like AM/FM signals, cellular telephones, televisions, other forms of communication. Sometimes I think Wi-Fi even is in the low radio wave range. Now beyond so coming in from shorter wavelengths from radio, we get microwaves. Microwaves have longer wavelengths than they're shorter wavelengths than radio, so they're more energy. Microwave light is actually efficiently absorbed by water, and thus if a substance has water in it and you shine microwaves on it, the water gets hotter, the water gets more energetic. That's what it means to be absorbed. So the water absorbs that microwave light and starts to rotate and bounce and move around and get more energetic. This heats up your food. Substances that don't contain water, like a plate, tend not to get hot in a microwave. Some dishes, though, contain substances that absorb microwave radiation. Most do not, but some do. All right, after microwaves, we get shorter wave infrared radiation. This is what we call heat. Heat is what you feel when you put your hand near something that's hot, and it's emitting infrared. All warm bodies, including human bodies, emit infrared. While it is invisible to our eyes, we can detect it with our bodies, and we can also use infrared sensors to detect it. This is like night vision technology. Some organisms are able to use this in their eyes. They think mosquitoes are able to detect your heat. Some snakes have pits in their face that let them essentially detect the body heat of objects, and visualize it and see it, or at least we think that. So maybe they see kind of the way that our infrared cameras can see. And then we use a computer to artificially color objects that are hotter as red and objects that are cooler as blue. So you can kind of see that here. It's interesting in this picture. Healthy dogs have cool noses, and there was a debate about that. This picture kind of confirms it. These dogs have cool noses when they are nice and warm. Even this one right here, right on the tip of his nose, nice and cool. Okay, moving on. So we get to the visible light. Now, visible light, of course, we know goes from red light to blue light, purple light. Now, visible photons don't damage biological molecules. These can cause molecules in our eyes to rearrange, which sends a signal to our brain. We have vitamin A, which is used to make retinol, a retinol molecule in our eyes. Retinol absorbs light, and when retinol gets hit by light, a double bond changes its conformation from cis to trans, meaning it changes its shape, and that is the signal that your brain needs to know that light is present. And so while visible light can cause molecules to change shape, they don't damage them. Now moving on to the next type of energetic light, or into the energetic lights, we would call these ionizing radiations or ionizing light. So between X-rays and visible light is the ultraviolet or UV light. This is the component of sunlight that produces a sunburn or a suntan, depending on what kind of skin you have. It's not as energetic as gamma ray or X-ray, but the ultraviolet photons do have enough energy to damage biological molecules. Excessive exposure to UV light can increase the risk of skin cancer, and cataracts, and it does cause premature wrinkling of the skin. Now, after UV, we have X-rays. We know what X-rays do. They pass through substances that block visible light, and we're able to visualize our bones because our bones don't allow X-rays to pass through them like our skin does and our clothes do. And so it bounces off of the substances that are inside our bones. X-rays can carry enough energy to damage biological molecules, and so with several yearly exposure to X-rays that you go through with the dentist office and maybe a broken bone isn't enough to cause any immediate damage. It does increase your risk of cancer, of some type of cancer. We have 200 or so cells in our body, different types of cells, and every one of them can become cancerous. So you got to be really careful with X-rays. The story of the guy who invented X-rays, or nobody invented X-rays, he discovered them. He actually died of X-ray exposure cancer, and he also, I would say, killed his wife. He used to take pictures of her, X-ray pictures of her hands until her hands developed tumors and she died of cancer as well. Very, very dangerous waves. And then gamma rays. Gamma rays are the shortest. These, again, are very, very dangerous. And sometimes we can actually use gamma rays as a way to, as a cancer treatment. So X-rays and gamma rays, called, we call it ionizing radiation therapy. We can shine these on parts of the body that are afflicted with tumors. Biological molecules get destroyed or sometimes changed. And since tumor cells are usually growing faster, they die faster. But this is still dangerous, and it does still kill healthy cells. And so while we do try to use gamma or X-ray therapy, it does have some side effects like fatigue, skin lesions, hair loss. And of course, that matters too on how long your treatment goes for. Which is hard because you're trying to target the tumor from multiple directions while trying not to hit healthy tissues. All right, so let's talk about each element has its own atomic emission spectrum of light. So we just talked about what light is and how light from the sun, composed of white light, has all kinds of different types of energies in it and different types of frequencies and different wavelengths. Now let's talk about how each atom itself has kind of a light fingerprint. So neon atoms inside of a glass tube actually absorb electrical energy and then re-emit that energy as red light. Anytime you see neon signs or neon that isn't red, it's not real neon, because neon, the gas or the element, emits light energy in the red spectrum. So that could be different gases, that could be mercury, or it could be hydrogen inside those blue tubes, or it could just be colored tubes. Painted. So here is light being emitted from a mercury lamp. It appears blue. Here's light being emitted from a hydrogen lamp. And it appears pink. If we take pure samples of gases, or of elements, and we put them into what we call a discharge tube, which ionizes them, has them pure inside of a light. It's essentially a light bulb filled with these gases of these elements. And when we put electricity through them, they all give off characteristic colors. So you could make neon, quote unquote, tubes out of different elements. Now, they all give off different colors. Now, why do they give off different colors? This has to do with what we're going to say is the arrangement of the electrons within their structure. Now, as white light spectrums are continuous, with some radiation emitted at every single wavelength, the emission spectrum of an individual element only includes certain specific wavelengths, and we would say that it is not continuous. So it is a not continuous or discrete spectrum as opposed to continuous spectrum. So white light from a hot object like the sun has all wavelengths in it, but atoms only have certain wavelengths. Now, when we take the pink light that comes out of the hydrogen atom and we put it through a slit to give it a shape and send that through a prism, we get a couple of different lines. I just messed up my whole picture. We get a couple of different markings. We get 4 unique lines, 4 specific wavelengths. Okay. We call this the hydrogen emission spectrum. There's a helium emission spectrum, a neon emission spectrum. Every element will emit a very specific frequency or certain frequencies of light. Now, this was what Niels Bohr was looking at and playing with. And he had this brilliant idea. He thought, what if somehow the reason that these certain light waves are coming out of these elements have something to do with the electron organization inside those atoms? And so this hadn't been done before, but he decided he was going to quantify energy. He was going to make energy come in chunks. Okay? So energy comes in chunks. I can't spell chunks. Chunks, yeah, just a K. And we'll call these H. We'll call these Planck's constant, H. So little bits of H. And so let's say that the minimum amount of energy is 1 H, just like the minimum amount of money is 1 penny. You can't have less than a penny, right? You can't have a half a penny. There's no such thing. Starts at a penny, and we can have multiples of a penny. So the minimum amount of energy is H, and so we can imagine that the longest wavelength of light possible only has the energy of 1 H. And that as we start to add more energy into light, light gets multiple H's worth of energy. Similar to how how money only has certain values, he thought maybe energy levels inside the atom also only have minimum or certain energy levels that were allowed. So he came up with this, what we call the Bohr model of an atom that has shells. Each of these shells surround the nucleus. The nucleus is in the middle, and we would number these. So the n equals 1 shell, the n equals 2 shell, the n equals 3, 4, and 5 shells. And that when we wanted to put electrons into these shells, they could only go into shells that they had the right amount of energy for. Just like on a ladder, you can't step anywhere you want. You have to step on the steps, right? And so that's kind of like the minimum energy requirements. If you're going to be an electron on the bottom level, you have an energy equal to 1. If you're going to be in the next level, you have an energy equal to 2. Or if this was H, this would be 2H, and this would be 3H. Now, it turns out that these levels of energy are actually much, much higher than the basic level of H. It's kind of like me saying, okay, things are all based on the penny, but this costs 5,000 pennies, this one costs 8,000 pennies, right? It's not the minimum energy, but it's still built on the minimum energies. So this is 5,000 H's and this is 8,000 H's. Okay, that's what the analogy is here. Now I'll tell you the real number of the energy level of these in a minute. But that was the idea, that they all have an energy level, that you can't go anywhere in the middle, anywhere in between. You have to have the energy of the specific energy levels to go between them. And if you were to move from, let's say, energy level 2 to energy level 3, you would have to gain that energy. It would require, in this example, adding another H. Or, if you wanted to go from n equals 1 to n equals 2, we need to find 3,000 H's, right? In this example of 5,000 and 8,000, in terms of value of energy, we need to gain 3,000 to be able to move from n equals 1 to n equals 2, or we need to lose 3,000 if we're going to go from 2 to 1. And those bits of energy would be given off in chunks. They would be just absorbed or kicked out, right? Let's try to imagine that. You're an electron hanging out at n equals 3. You want to jump up to n equals 4. So you got to gain some energy. What if there was a specific frequency of light that had the exact energy that you needed? That would give you the energy you needed to jump. And now you've jumped up. But now you're an excited electron that's in a higher energy than it wants to be. So now you want to relax again. You're going to drop back down. You can drop back down to n equals 3, or maybe you drop back down all the way to n equals 2. Depends, whatever you're feeling. But when you do that, you're going to kick out another photon to carry away that energy that you don't need anymore. These photons being ejected from the atom correlate to these photons that we're seeing. That's exactly what's happening. When electrons absorb a photon of light, they jump up to a higher shell, one that's equal exactly to the number of energy that they just got. And it's not like they get to make all the shells they want. Every atom has a specific set of shells. And so, in order for those electrons to actually move between those shells, they absorb very specific kinds of light. So now imagine a t-shirt that looks red, yet white light is shining on it. Well, why does it look red? Maybe the red light can't find an atom, or the red light can't find any atoms that have any electrons that want that light. No electron can do anything with the red light. So it just comes in and it bounces off of the surface of the shirt or the molecules. But every other color, whether it's blue or green or yellow, is finding electrons that are willing to absorb that color and jump up to a higher shell. Now, that's what's happening. Reflecting, absorbing, each molecule, each atom that has electrons is able to do this. So start putting different materials together, you start to see that if you have enough different materials, hey, you're going to get a black shirt because every color light is going to get absorbed. Think about a white shirt. No electrons are being energized, and all light is being reflected, and it still looks white. So that's kind of neat to think about. Okay, so it turns out that when the hydrogen atom absorbs energy, electron is excited to a higher state, and when it relaxes, it emits that photon back out. Now, since the amount of energy in a photon is directly related to its wavelength, the photon has a specific wavelength. Now, the light emitted by excited atoms consists of specific lines at specific wavelengths, and each corresponds to a specific transition between two orbits. So, for example, the line at 486 nanometers corresponds to the electron relaxing from the n equals 4 to the n equals 2 orbit. Because when we go and find out the energy, now I didn't give you any energy equations, we do have the energy of a photon is equal to Planck's constant times the frequency, or equal to Planck's constant times the speed of light divided by the wavelength. This is how we get frequency. It's speed of light over wavelength. Planck's constant is 6.626 times 10 to the minus 34 joules. It's not a lot of energy. It's a very, very tiny number. But we can multiply that by a frequency to know an energy value. Another thing that we do is we can actually figure out, if we know the energy, we can figure out what wavelength of light that would have to be, right? Because if we know the energy and we know what Planck's constant is, i.e., the penny, the basic unit of energy, then all we would solve for is frequency, which we could then turn into wavelength. So we've got two things here. We're able to use the light energy coming off of atoms to turn that into energy information, or the light wavelengths, the color of light. We could find out their frequencies and wavelengths and use that to figure out the energy differences between the atomic electron orbitals. That lets us kind of back figure out what the inside of the atom looks like, because we didn't know that there was an n equals 5 and 4 and 3 and 2 shell, but by seeing that light from these different types of light coming out of this atom tells us that these different transitions are possible, 5 to 2, 4 to 2, 3 to 2, and it also lets us calculate the amount of energy in each of these transitions. So then we can go back and know how much energy there is in every one of these energy levels. Now, for the hydrogen atom, this is a really huge breakthrough, great success. Now, however, this failed to predict the emission spectra of other elements that contain more than one electron. And for one of the reasons is electrons interact with each other. So for this and other reasons, the Bohr model was replaced with a more sophisticated model called the quantum mechanical or the wave mechanical model. So for the Bohr model, it only works for hydrogen because there's only one electron in its orbit. For helium, which has 2 electrons, and neon, you can see more electrons starts to give us a more complicated picture. Now, that being said, we use light telescopes when we point them at other planets in the sky, and we use prisms to separate the kind of light, and then we use computers to analyze the different spectras to see if we can figure out what the atmosphere is made up in those planets. So that's how we find out that there are, planets that contain carbon dioxide or planets that have water in their atmospheres. Okay, so the quantum mechanical model is atoms with orbitals. Now, the quantum mechanical model replaced the Bohr model, and we replace the Bohr orbits with something we call orbitals, quantum mechanical orbitals. Now, orbitals are different from the orbits in that they represent probability maps that show a statistical distribution of where the electron is likely to be found, which is a little bit different than just saying it's in this circle, right? In the Bohr model, we were like, oh, it's in n equals 1. Well, now we can say it's in this area. So let me kind of explain these pictures here. So in quantum mechanics, we are unable. Here, how do I say this? Quantum mechanics revolutionized physics and chemistry because in the quantum mechanical model, electrons do not behave like particles flying through space. They don't behave like a baseball flying towards, the batter. I don't know what I want to call that. The batting box. We cannot, in general, describe their exact paths. An orbital is like a probability map that shows where the electron is likely to be found when an atom is probed. It doesn't represent the exact path that an electron takes through space. So contrast the behavior of a baseball with that of an electron. A baseball thrown from the pitcher's mound to the catcher at home plate, the baseball's path can be easily traced as it travels from the pitcher to the catcher. And if we knew the forces on the ball, the force that he threw it, the force of gravity downward, the air resistance, all that kind of stuff, we could actually predict exactly where that ball would go. That's called a deterministic model. That's what Newton's laws of gravity and all, being able to track the planets and stars, all of that stuff, we're really good at seeing. Anything we can see with our eyes, we can track it, no problem. The problem comes up with things that we can't see, that we don't really know where they are. So in the quantum mechanical model, the catcher wouldn't know where the electron would cross the plate for any given throw. He would have no way of knowing where to put his mitt in the right place. But if the catcher kept track of, let's say, hundreds of electron throws, he could observe a reproducible statistical pattern of where the electron crosses the plate. He would be able to say, yeah, there's a good chance, 20% that it'd be here, 40% here, 70% here. He could draw these probability maps in the strike zone and actually show where the electron would be at what percentage of the time. And these are called probability maps. Okay? And so probability maps are what we're going to develop now for the quantum mechanical model. So in the quantum mechanical model, a number and a letter specify an orbital. So the lowest energy orbital is going to have the lowest energy, which is or 1, n equals 1, and then it'll have the letter S. And S here will be the first, let's see, the first number is the principal quantum number. So that's these. These are the principal quantum numbers, and they're designated N, and they specify the principal shell that you are in. And so a single electron in an undisturbed hydrogen atom at room temperature would be in the 1s orbital. So I'm going to throw an S in here, 1s. 1s orbit, this would be the ground state. Now, the absorption of energy by the hydrogen atom can cause this electron to jump or make a transition from the 1s into a higher state. And if it jumps up, we're going to say it's in an excited state. If all of the atoms of each element have one ground state, all of the elements have one ground state, but they can have many excited states. Okay, there's always one ground state for every atom, for every element. But they can always be excited. They can always jump up. So the higher the principal quantum number, the higher the energy of the orbital. The possible quantum numbers are one being the lowest and then going up and up and up. And so since 1 is the lowest number, it has the lowest possible energy. Now, the letter will indicate the subshell of the orbital and actually specifies its shape. And we do have, let's see, I thought I had them written out. Here are the orbitals. There's S, P, D, and F. Now again, we can have subshells in every orbital. So n equals 1 has an s subshell. N equals 2 actually has an s and a p subshell. N equals 3 has an s, a p, and a d. And n equals 4 gains an f subshell. So the higher energy levels have additional subshells. The subshells, though, also designate shape. So orbitals are sometimes represented by dots, where the dot density is proportional to the probability of finding the electron. The dot density for the 1s orbital is the greatest near the nucleus, and it actually decreases the farther away you get. So the electron is more likely to be found close to the nucleus than far away from it. Now orbitals can be represented as geometrical shapes that encompass most of the volume where the electron is to be found. So the 1s orbital can be represented as a sphere in which the electron is 90% of the time found within that volume. If we superimpose the dot representation of the 1s orbital on the shape representation, we can see that most of the dots are within the sphere, meaning that the electron is most likely to be found within the sphere of the 1s orbital. You can see that there are some electrons that sometimes we will find outside the sphere. But this is the best we can do with the probability densities. Okay. So again, the numbers of subshells start with 1, they go up. The number, the principal energy number starts with 1 and go up. And then as far as the number of subshells that we get, you can see that also increases. It increases to a number of 4. We don't have this going on infinitely, though there is a G subshell that some people talk about when they deal with their with some of the high number elements like 118 and stuff like that. But we're not going to go into that. Okay, so the number of a subshell in a given principal shell is actually equal to the value of n. That being said, if we were to go to n equals 7, there theoretically could be 7 subshells, but we will be able to deal with all of our atoms using these 4. Okay, oh, and I had another image here. The 2s orbital and the 1s orbital for comparison. Since they both have s orbitals, subshells, they have the same shape. But because the 2s orbital is higher in energy, you can see it is also bigger in size. That being said, all of these orbitals are going to contain inside them the lower energy level orbitals. Our atoms are all spherical, we think. So this 1s fits inside the 2s, and then if there's a 3s, it'll go on the outside of that. All of the subshells within the same number would fit within the same area. So a 2p orbital would also be found within the 3s to some extent. We're going to see that their shapes do play a part here. All right, and as far as the s orbitals go, they're spherical. Let's take a look at some p orbitals. The p orbitals are sort of, I don't know, dumbbell shaped. You can imagine tying 2 balloons together, sort of. So we get 3 different p orbitals. P orbitals here line up along the 3 different axial directions. So along the x-axis, along the y-axis, along the z-axis, but they are all identical to each other in every other respect. Something that we could be talking about already is that orbitals of any kind can only hold 2 electrons. So that means in each of these s orbitals we can get 2 electrons, right? 1s, 2 electrons, 2s, 2 electrons. And then in the p orbital, we're actually going to be able to fit 6 electrons total, because each of these orbitals will hold an electron. Okay, and there's our p orbitals. We've also got some d orbitals. The next principal shell is n equals 3. 3 subshells, s, p, and d. The d subshells actually have 5 different orbitals. And so you can see here those different shapes. Now we're not going to go through all of the shapes of all the f orbitals, because those, I don't even have a picture of them, but you can look them up. They're not even worth looking at. There's just gibberish like this. This is just gibberish. But you can see that they are, again, different planes. This one has a little bit of a different shape. The f orbitals get really crazy looking. But these are density probabilities, or probability densities. Every time we look to see where the electrons are, they tend to be in these areas, and then we can kind of draw these shapes that represent kind of like the cloud that we would see them. Okay. From orbits to orbitals, the quantum mechanical model predicts that the bright line spectrum of hydrogen, as well as the Bohr model does. The quantum mechanical model predicts the bright lines of other elements that Bohr model cannot predict. So the Bohr model got replaced with this more sophisticated model, and the Bohr model, though, is still important because it does provide a logical foundation to the quantum mechanical model, and it kind of reveals the historical development of the scientific understanding. So let's talk about how electrons actually occupy orbitals. They do this in something we call an electron configuration. This shows the occupation of orbitals by electrons for a particular atom. The electron configuration for a ground state hydrogen atom is as follows: 1s, 1. The electron configuration tells us that that hydrogen's single electron is in the 1s orbital. This number here off to the side, this exponent, is the number of electrons. Another way to represent this is with an orbital diagram. So orbital diagram. And an orbital diagram, again, uses a box and an arrow to represent this. Now this is a 1s box, so this just represents the orbital 1s, and the up arrow is representing the electron. Now, electron spin is a fundamental property of electrons. They can point up or down. We say this has its electron, it can be spin up or it can be spin down. Now, there's something called the Pauli exclusion principle that states that no two electrons with the same or in the same orbital can have the same spin. So they have to have opposite spins. And so when we pair up electrons, we often show one up and one spin down. Now, energy ordering of multiple electron atoms is a little complicated. So there are different subshells within the same energy level, but these don't have the same energies. And the reason they don't is because of electron-electron interactions. Electrons can repel each other. They can also shield each other from the positive charge at the center of the atom, right? Not every electron gets to feel the same positive. The ones that are closer, they feel more of that positive. The ones on the outside, they don't really know there's a positive in the middle as much because of all the negative electrons in their way. So because of these things, and because of the shapes of the orbitals, which leads to something called penetration and shielding, we get different energy levels. And one of the results is that the 4s energy level is actually lower in energy than the 3d energy level. It should go 1s and then 2s and then 3s and then 4s, but it doesn't. It goes 3s, 3p, and then 4s, then 3d. It drops back down. Then it goes 4p, 5s, 4d. So the 5s drops in before the 4d does. And so there's a little bit of some out of order stuff in here. So it's important to pay attention to that. I'm going to show you how to kind of solve that for yourself. If you do this sort of step ladder, you write 1s and then 2s, 2p, and then 3s, 3p, 3d, 4s, 4p, 4d, 4f, right? And you do this, and then you follow this little zigzag pattern. It tells you the order of the filling up the electron configurations. Of course, if you can kind of follow this one helps too. Okay, so when we are filling in electron configurations, this is what we do. We start with the number of electrons total. Helium has 2 electrons. The electron configuration for helium would then be the 1s orbital and then the 2 electrons. And now we're done putting electrons in. So that would be the ground state electron configuration for helium. If we wanted to do this for lithium, lithium has 3 electrons. So we would say, okay, where do those go? The first 2 are going to fill up our 1s orbital. Well, then we can't put any more electrons in there, so we have to go to the next highest energy level, which is the 2s. It always fills in from the bottom up, low energy to high energy. Atoms always want to be the lowest energy they can be. So this requires us to put in an electron into a new energy level. It's the 2s, and then this one would hold 1 electron. Now we always stick electrons in spin up, but they don't have to go in as spin up. They can come in as spin down as long as they are not the same spin as their other electron. As convention, though, we always go spin up, then spin down. And this is more important in Chem 1 than here, because in Chem 1 you want to assign quantum numbers to every electron, and that depends on spin. And so if you put the wrong spin down, let's say before spin up, you're going to get a different quantum number. Let's do another one of these. Let's do carbon. Carbon has 6 electrons. We know that from looking at its atomic number. The 1s fills up after 2 electrons. The 2s fills up after 2 more electrons. That leaves 2 additional electrons for carbon. So it goes to the next energy level after the 1s and 2s. It's the 2p. And remember, the 2p can hold more electrons because there are actually 3 types of orbitals in the, or 3 different subshells, p subshells. We show that by expanding the number of boxes. So if I wanted to keep going in this direction, it would be 1s, 2s, then 2p. Then I would do a 3s, and then a 3p. Then it would be a 4s, because 4 comes after 3p. And then it would be 3d. And 3d, if you remember, there were 5 d subshells. So you'd want to show all of 5 of the 3ds. There is 7 f subshells. There's 7 that we didn't look at. So there's 3 types of p, 5 types of d, and 7 types of f. All right, when we are sticking in electrons now into a p orbital, notice that I didn't do this for carbon's 2p electrons. I didn't put them into the same box, the same orbital. And you can imagine electrons having the same negative charge as each other don't want to be next to each other, so they get spread out a little bit. So they get separated. We call it Hund's rule. Hund's rule states that electrons will file into different orbitals singly before they go into any parallel spins. So they'll spread out before they double up. Now you can look at this and get the order: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, and after the 6s, it goes 4f, and so on. But we won't go really that far into the periodic table. All right. Lower energy orbitals fill before higher, no more than 2 electrons in the same orbital, and only pair up electrons after they've been spread out first. And so you can see here from the next 4 electron configurations how that would look. So number of electrons, 7, 8, 9, 10. We can see here that nitrogen has 1 more than carbon, so every orbital here has an electron in it. Oxygen has 1 more than nitrogen, which means we have to double up now. So we go back to the first block and start putting in down electrons, just like we did when we got to these, right? We filled these up before we moved on. Fluorine only has 1, and then neon, of course, is completely full. So when we get to neon, let's talk about how neon is a noble gas. So noble gases, when we're writing electron configurations for elements beyond neon, or beyond any other noble gas, the electron configuration of the previous noble gas can actually be abbreviated. So let me show you what I mean. Let's say that I want to write for sodium. Sodium has 11 electrons. So sodium is basically everything that we see for neon. It's 1s2, 2s2, 2p6, because that's where you would put 10 electrons. And then sodium is 3s1. So that's sodium right there. Now, we could make this a little easier on ourselves when we're doing this by just saying, hey, since sodium has everything that neon has in it, we could just say it's neon, in brackets, plus 3s1. And this works for any of the other noble gases as well. After sodium is potassium. So we can say that potassium is just argon. with 4s1, right? We can do that. All right, it looks like I'm going to lose my power on my iPad, so I'm gonna charge up my iPad and I will finish this video after that. All right, so we can get into a little more specific terms when we talk about these electrons. We can say that they are core electrons if they are on interior subshells, and they are valence electrons if they are on the outermost subshells. And what we use to decide that is actually the principal quantum number. So whichever shells have the highest principal quantum number, those are going to be our valence shells or our outermost shells. These are the electrons that are important in chemical bonding. The electrons that are not the outermost electrons or in the outermost principal shell, those are called core electrons, and those electrons do not participate in the chemical bonds. So what we'll end up seeing is that there is a lot of similarity in the valence electrons between elements within a column on the periodic table. So silicon, for example, has 4 valence electrons, and those are in the n equals 3 principal shell, and it has 10 core electrons. This is the electron configuration for silicon. This is what we would have written if we were writing it out. 1s2, 2s2, 2p6. That would be, you'll notice that most of the core electrons end up making noble gas configurations. This is neon, and then silicon is 3s2, 3p2 beyond that. And again, this has to add up to the 14 electrons that silicon has. Let's do another one. Selenium. Selenium is in the periodic table right underneath sulfur. So because it is right underneath sulfur, and sulfur is right underneath oxygen, whatever valence electrons oxygen has, we would expect selenium to have the same. Let me remind you, oxygen has 8 electrons, 1s2, 2s2, sorry, not 8 electrons, it has 6 electrons, 2p, no, it does have 8, I'm sorry, it does have 8, but the p shell can hold 6, and there's only 4 of those that go in here. So if we look at its valence shell, we see that it has core and valence, with the higher number being 2, and then in all of those valence shells we have 2, 4, or 6 electrons. If we look at selenium, we see selenium also has a highest shell that is the 4s and the 4p, and within those we see also 6 electrons. So the number of valence electrons happens to be what the commonality is within each column of the periodic table. This is what makes hydrogen and all the elements under hydrogen that reactive. This is what makes the noble gases, which all have full shells. That's the other thing here. The 2 can only hold, the S can only hold 2, the P can only hold 6. So when we look at, neon, sorry, my E is a little big there, or argon, which would be everything up until the 3s2, 3p6, we see full shells, full shells, full shells. All right. So electron configurations in the periodic table are related. The elements within a column all have the same number of valence electrons and similar outer electron configurations. So 1s2, full shell, 2s2, 2p6, 2 full shells, 3s2, 3p6. Now these are just the outermost. These aren't argon's only electrons, 3s2, 3p6. Remember, this builds on itself. So for example, in order for helium to have 1s2, it had to first come from an element, or nature, when it puts together elements, doesn't make each element that unique from each other. They're just bigger and bigger elements made out of the same parts. So a helium is essentially a hydrogen scaffolding that has an extra electron in it and an extra proton in it and some other neutrons in it. Of course, we're not talking about how protons go into the nucleus. That is a whole other course. And they do have their own orbitals and energies and all that, but we're not going to go into any of that detail or even talk about it ever again in this class. But for electrons, we do talk about it. An electron scaffolding, or the way electrons go into the outside of atoms, is the same for all atoms, and it is the simplest in the 1s1. It builds to the 1s2, and then the next row of the periodic table, the 2s and the 2p, you can see they fill in one at a time. 1 electron, 2 electron, 3 electrons, 4 electrons, 5, 6, 7, until we get to the full shell of 8. Now, we usually talk about an octet. We'll talk more about it in chapter 9. Chapter 10, I think it is, when we look at chemical bonding. But here it's a good place to start thinking about octet. Octets are these stable configurations where you have 8 outer electrons, and in molecules as well as in atoms, that's an important number. We see again in this third row the 3s and the 3p electrons. Now we can expand this to the whole periodic table, and you can see here that the first 2 columns on the left-hand side are the s block. So every atom that's in these 2 columns is going to have their outer electron in the s block. Hydrogen only has 1 electron, so it's already only in the s block. But lithium has 3 electrons total, and 2 of them are in the s block, but they're also in a lower orbital. They're in the 1s block, and then the last outside electron is in the s block. So for all of these guys, for lithium, that's another bad example because there's no core electrons that are in different orbitals. But let's take, potassium, for example. Potassium has a lot of core electrons. It has 1s2, 2s2, 2p6, 3s2. You can see where I'm going with this. 3p6. All of these electrons are still within potassium, but its outermost ends up in the s block. The 6 columns on the right-hand side make up the p block. The transition metals are the d block. The lanthanides and actinides are the f block. Let's see. There are some trends. We're going to talk about the trends. I'm trying to remember if there's one more thing I wanted to say here. When you're writing electron configurations, you can simply follow across the rows to get to the element that you want, and then just read off the full numbers. Let me give you an example. Boom. Let's just do that one. So I'm going to just write the electron configuration up to this point. So I'm going to go through the 1s block, and then I'm going to get to the 2s block, and then the 2p block. Then I get to the 3s block. Next is the 3, because I'm in row 3, p block. Then I get to the 4s block, and then the D shell. Now, even though the D shell comes in the 4th period, we got to remember that D shell belongs to the 3rd group, not the 4th, because of the way that the energies are kind of distributed. So 3D comes next. So a good rule is the D block is always n minus 1. So if I wanted to number these D blocks, I'd look at the row it's in. This is a 6, so this is the 5D. And you can see that there. 5D, 5D, 5D. For the F blocks, it's always n minus 2. So you'll notice this is the 4F3 block, even though it would be in the 6th period where we find this column or this row of elements. So you can use the periodic table like that. Okay, the number of valence electrons for any main group element is equal to the column number. So 7a, 7 valence electrons all the way down. The row of the periodic table is equal to the highest principal energy shell. So, for example, even though iron is the 3D, that's not its highest electrons. Its highest electrons are in the 4s2, which is the same as the number row it's in. Okay. Now, the main group elements are different than the transition elements. The transition metals have electron configurations, trends in them that are different than the main group. The principal quantum number of the d orbital being filled across each row is equal to the row minus 1, and for F's it's minus 2. There are some odd electron configurations that we see in the D block. For example, one of the exceptions that we see is that chromium, right here, doesn't follow the trend of being 4s2 3d1, 4s2 3d2, 4s2 3d3. It should be 4s2 3d4, but it's not. It's 4s1 3d5. And it makes more sense when we look at the orbital diagram. So here's 4s2 3d 3d4. So that's what the orbital diagram looks like for chromium if it followed the trend. Now, instead of following the trend, it does this. Now, the difference is it doesn't have any paired up electrons, and so that actually lowers its energy. Pairing up electrons, putting charged things together that have the same charge, that creates energy or barriers of energy. And so by having these electrons fill out or spread out, it fills up, rather than having a full S shell and an almost full D shell, we get half full of these shells all around, and that's more stable. The other exception is copper. This should be 4s2 3d9. So 4s2 3d9 would be missing one electron from this last orbital, but instead it fills that orbital and just leaves the s orbital unfilled. And so again, having a full D shell and a half full S shell compared to a full S shell and an almost full D shell, nature makes some exceptions. Okay, so I was just mentioning that there are some exceptions in the transition series. Those half-filled shells are particularly stable. Okay, and I was mentioning you can use this periodic table sort of S, D, P, and F block as a way of getting to your electron configuration. So if you were after phosphorus, then we have to just, follow the rows until you get to where you want, and then you count. 1, 2, 3 into the P block is P3. Anyways, you should practice those. Now, you can write the electron configuration for any element based on its position in the periodic table. Let's write some, I wanted to do some examples of some ions because sometimes you guys don't get enough examples of that. Let me see if I have an example in front of me. I don't. So let me do an example. So what about a periodic table or a configuration for, let's say, germanium 4+. So if you are writing for an ion, let's do two. Let's do a negatively charged one and a positively charged one. Let's do I-. The good thing to remember when you're doing these is that the number of electrons is going to be reflected in the charge. So if the charge is neutral, then your number of electrons is the same as your protons. But if you have a charge, then you need to think about what that means for your electrons. In the case of iodine minus, this means we have one more electron. Iodine has 53, so we would now have 54 electrons. And the best way to do it is just to write out the normal electron configuration for iodine and then come back and add in one more. So for example, iodine would be 1s2. Let me see what row iodine is. Iodine is in row 5, so it's 5s2 4d10, 5p5. So that would be regular iodine, and now we're writing it for I-, so we add in an electron, 5p6. Note that I- has the same electron configuration as xenon. And that's important too. We're going to see that when molecules form charges, when ions form, they form in such a way that gives the element an electron configuration just like a noble gas. I don't want to do germanium anymore because he's one of those group four elements that can be positive or negative. Let's do one that's a little more something we would know. How about calcium 2+? So this is from column 2 of the periodic table. We know that column 2 is always form a 2+ charge. Let's just put in all 20 electrons for calcium and see what we've got. So calcium is in the 4th row, so 4s2. I think that's 20. So calcium 2+ is missing 2 electrons. So calcium 2+ would not have those outer electrons, and that's the point I'm trying to make. Whenever an ion forms for a metal, they lose their outermost electrons from their outermost or their largest energy shell. So in the case of calcium, that comes from the 4s shell. This would go to 0, or you could leave it off completely, and you'll notice that calcium 2+ has the electron configuration of argon. Now let's do one of those transition elements. Let's do iron. Iron has an electron configuration that has 26 electrons in it, but iron 2+ would not have that same electron configuration. So iron 26, or regular iron, 1s2, 2s2, 2p6, 2p6, 4s2, 4, sorry, that wouldn't be a 4. That would be a 3d. And iron is 1, 2, 3, 4, 5, 6 in. So that would be regular iron. Now, iron 2+, we're going to remove 2 of the electrons from its outer shell. That means from the 4s shell, because those are the outermost. 3d is the last thing we wrote, but those are not the outermost. And then if iron was actually iron 3+, and we had to take off another electron, then it would come from here and it would become 5. So that's what you do when you are adding electrons for negatively charged ions or removing electrons for metals. You take it from the outermost shell, and in the case of transition elements, sometimes that's not the last thing you wrote. Okay. So, what did I want to say about these noble gases here? So the calculations show that atoms with 8 valence electrons, or 2 for helium, because helium only has 2, are predicted to be particularly low in energy and therefore stable. The noble gases are chemically stable and thus relatively inert or non-reactive as accounted for by our quantum model. Elements with electron configurations close to the noble gases are the most reactive because they can attain noble gas electron configurations by simply losing or gaining a small number of electrons. So the alkali metals, these are the most reactive metals since their outermost electron configuration is ns1. It's just 1 electron beyond a noble gas configuration. If they can react to lose that electron, they can attain a noble gas configuration. So this explains why group 1 metals tend to form +1 ions when they form ions at all. And hydrogen isn't shown here. Hydrogen's right above it. And again, hydrogen also forms that +1. Now, when potassium is in its positively charged form, it's very stable. This is how you find it in salts. This is how you find it in, ion form in our body, the way that we use it. But as an elemental solid, very reactive. The alkaline earth metals, these are all group 2. They all have ns2 configurations, where n is just the row they're in, and therefore 2 electrons beyond noble gas. So when they react to lose 2 electrons, they form 2+ charges, and they attain noble gas configurations. So this is explaining why this happens. Halogens, these guys are all ns2np5, so 1 electron short of a noble gas configuration. what did I write? NS2NP5, where N is just the row that they're in. So these guys tend to gain one electron, forming -1 ions, and of course these are why we see those. Now I skipped over a few rows here. Row 3 is 3 beyond a noble gas, so it loses 3 electrons. Nitrogen in this column 5 is 3 away, so these guys tend to form 3 minus charges. These guys in row 6 or column 6 are 2 away. And column 4, they are right in the middle. So sometimes they form +4 or -4. This is what makes them good at either being conductors or insulators. They sometimes will lose electrons, sometimes they won't lose electrons. And they're right in the middle, sort of undecided. All right, let's go over the trends. As you, so some of the trends, so there's 3 trends, sorry. One of the trends is size. One of the trends is ionization energy, and the other is metallic character. So let's talk about size first. As you move to the right across the periodic table, the atoms get smaller. Now the atom size is determined by the distance between the outermost electron and the nucleus. And since the orbital isn't changing, this is the 2p orbital for all of these guys here. Well, this is the 2s right here, but for the rest of this row, they're all in the 2p. What is changing is the number of protons. Neon has 10, fluorine has 9, oxygen has 8. As you get more and more protons, that's more positive, more pull. And since they're all in the same row, they get pulled tighter and tighter the more protons you get, so the atoms get smaller and smaller. As you go into each new row of the periodic table, so as you go down a column, they get bigger. And of course, this should make sense because as you go down a column, you're adding a whole new sort of principal energy level. It's like adding another floor to your house. So as we also see them getting bigger because of the distance from the nucleus. All things being equal within a column, as they get farther and farther away from that positive charge at the center of the atom, the attractive force between those electrons and protons gets weaker and weaker, meaning that those electrons can kind of pull away further and further away. So they get bigger as you go down. It gets smaller as you go to the right. All right. Now let's look at ionization energy. Now for ionization energy, there is 2 trends. There's the increase as you move to the right, and there's a decrease as you move down a column. And this is an inverse of the size. And what this ionization energy is telling us is how much energy does it take to put into this atom to get it to ionize. And we mean like potassium becoming K plus and removing an electron. This is like what ultraviolet light does. Ultraviolet light ionizes you, knocks off your electrons. Visible light comes in and doesn't have enough energy to do it, but ultraviolet light, X-ray, gamma, those come in and knock our electrons off. So, and that'll be important later. We'll talk about why in a different chapter. Wait, will we? No, this is in Chem 1. In Chem 1, we would talk about Einstein's experiment and how he figured out the photoelectric effect. And actually, that's a good... I need to mention that because we've been talking about the... and that's it right here. We just talked about it. The photoelectric effect is when you shine light of a certain wavelength on metal, electrons start being emitted from the metal. And that tells us that, well, we can do this for all kinds of metals, and we can see that they all hold on to their electrons differently, and that it takes different amounts of energy light to strip electrons off of different metals. But what it tells us also is that one photon can interact with one electron. A photon with a certain amount of energy comes into the metal, and an electron gets ejected. 1 to 1, just like that. So that's where light, which normally is just a wave, has particle nature. So light acts like a wave and a particle. Now electrons act like particles all the time, but they also act like waves. They move through materials like waves, and they have diffraction, and they do things that light does. And I just always love talking about this stuff with Chem 1 because we have lots of images to look at and stuff. But in Chem 20, that's not really a subject of our book. But I know I had kind of prefaced this chapter and this lecture with the particle and wave nature of these two things, light and electrons. Maybe Google it or YouTube it. Not the photoelectric, the double slit experiment. When we send light, a really dim light down long distance and force it to go between one of two slits, we see that the light has to choose between going through one opening or the other, and it still somehow interferes with itself. And that's really weird. That's what waves do. Electrons are these little particles, and yet they interfere with themselves too. And not just electrons. We've sent molecules as big as carbon-60, which is giant, right? One carbon proton is 2,000 times bigger than an electron, and carbon has 6 protons in it. Imagine 60 carbon atoms all together in this cool little soccer ball shaped molecule. They're called Buckminster fullerenes. Anyways, they make these big carbon balls, and they send them in rows at these double slits, and the carbon atom has to go between one slit or the other. When we're watching to see if the carbon went through slit A or slit B, then on the back of the screen at the detector, they only make 2 lines. Like they either go through slit A and hit where A slit is, or they go through B and hit where the B slit is, and they leave a little pattern that looks just like the slit. But when we're not looking, when we don't have a way of knowing which one they went through, then they leave a diffraction pattern, which means there are alternating black and white lines where they're hitting. They're hitting everywhere. They're interfering with themselves. And that's really weird that matter does that. That matter is a wave. Yeah, our book doesn't go into it as much. It's kind of disappointing. So I got out on a tangent there. I'm sorry. Ionization energy is when electrons get stripped off of materials, and it's the energy required to do that. You could imagine that lithium and beryllium being this close to, or having too many electrons, would want to get rid of their electrons, right? We just said that they like to lose their electrons to look like noble gases. We know that these guys, being close to neon, really want to gain some electrons to look like neon. Of course, this is why we say things are metals and nonmetals. Metals lose electrons and nonmetals gain them. But if it's so much, if these guys, lithium and beryllium, don't want the electrons, then you can imagine that the ionization energy, the energy required to remove electrons, would start off low over here and get higher as we go this way. And that's exactly what happens. Ionization increases across a row because it's really easy to get rid of electrons in the beginning of the row because they don't even want their electrons. They want to get rid of them. So the energy required to take them off is really, really little. So if that makes sense, then it should also make sense that as you go down a column, it gets easier and easier anyways, because your electrons are farther and farther from the inside of the nucleus, right? Lithium's protons and its electrons are right there, but potassium's protons and electrons are, separated by many shells, and so the farther away the electron is, the easier it is to strip off that electron. So this part of the trend goes hand in hand with the size trend. Actually, these are the exact same arrows. Sometimes I like to say with size that it gets bigger going down and bigger to the left, because it makes more sense to talk about one direction rather than say it goes bigger one way, smaller another way. So bigger down, bigger to the left. With ionization energy, this one is bigger. It gets bigger up and bigger to the right. So it's the opposite of the size trend in terms of the size, like getting bigger. And that should make sense. As you go up a column, atoms are getting smaller, so it's harder to take their electrons away. So the energy is higher. The ionization energy is the energy that it takes to remove the electron, that you have to put in to remove an electron, right? Try to think of ionization energy as like trying to take off the lid of a jar that's stuck, right? Some jar lids are easy. Those have light or low ionization energies. Some jar lids don't come off and you have to break the jar in frustration. That's a really high ionization energy. That's neon. Neon doesn't want to get rid of electrons at all because neon's already perfect. So those would be the ones that don't open. Okay, metallic character. Metallic character is basically just repeating what we've just said. These things, these size and ionization trends lead to the effects that we call metals and nonmetals. Metals lose their electrons and nonmetals gain their electrons. So as you move this way, As things get smaller and ionization energy gets bigger, we get more towards the non-metal side. And as we move this way on our periodic table to where elements are getting bigger and where elements have less ionization energy, where they actually want to get rid of their electrons, we call that more metallic. And so if we wanted to say more, we'd say more metal down, more metal to the left. So this would be the exact same trend as the size trend. So metallic follows size. And you can even say the bigger an atom is, the more metallic it would be. All right, before we end that, let me ask you guys a couple of questions. Or let me give you an idea of the kind of questions I might ask you. So maybe it's better to go back here. So let's go to the size one. I guess this is it. So what if I said, which element is bigger, sulfur or oxygen? So you would have to find them, relate them to each other. These happen to be in the same column, so you'd have to know lower in the column is bigger, sulfur. Or if I said, who's bigger, aluminum or, calcium? So you'd say, okay, here's aluminum, here's calcium. I know they get bigger going down, so gallium would be bigger than aluminum, but is gallium bigger than calcium? No, because they get bigger going this way too. So calcium's bigger than gallium, and gallium's bigger than aluminum, so of course calcium is bigger than aluminum. That's kind of like the logic that you could think about. One of the other things that's neat to think about is what happens when they ionize. Now, that's not within the scope of this class, but I'll just tell you guys anyways. Ions are also different sizes. Positively charged ions are smaller than the neutral element. So, for example, sodium might look like this, but sodium plus, here, that was bad. Na plus might look like this, where Na might look like that. And that should make sense. When you lose your outer electron, you look a little smaller. On the opposite side over here, chlorine might look like this, but chlorine minus might be slightly bigger. And that's because when you add another electron to your outer shell, they're going to repel each other a little bit. And you haven't increased the number of protons at all. That's stayed the same. These guys have the same number of protons. So more negatives in here mean they're going to kind of fluff up a little bit. This is how your body is actually able to distinguish between Na plus and potassium plus and all of these different ions in your body. They all are different sizes. Similarly, with ionization energy or metallic character, I could ask you a question. What has more ionization energy, phosphorus or selenium? You could look at phosphorus, you could look at selenium. If they're diagonal to each other, you have to think about what the opposite changes are. It decreases going this way, but then it increases going that way. Seems like those two things offset each other. It'd be hard to tell. These might be the same. On the other hand, germanium and phosphorus, it increases going down. I said that wrong. It decreases going down. It also decreases going this way. So 2 decreases is going to give you a good answer. Which one of these has the higher ionization energy? It'd be phosphorus, between phosphorus and germanium. But if it was between phosphorus and selenium, decreases and then increases kind of offsets. And so if they're directly diagonal to each other, we might say that they're the same. This is true for size as well. Which is bigger, oxygen or chlorine? Well, they get bigger, but then they get smaller. They're probably the same size. Or it's hard to tell. Now, if they're more than a row apart from each other and still diagonal, well, then there's no question. If we're talking about size, krypton is bigger. If we're talking about ionization energy, then oxygen's is higher. But if they're directly diagonal to each other in a direction that offsets, so down and then up in terms of the energy, or bigger than smaller, if it's not the same thing, bigger, bigger, smaller, smaller, then we won't be able to tell when they're directly diagonal to each other. All right. So in review, we talked about light. electromagnetic radiation that has wave-like and particle-like properties in the sense that one photon can interact with one electron and cause it to jump up to a higher energy level or to kick it out of an atom altogether. The Bohr model let us look at the emission spectrum of hydrogen and explain what electrons are doing and maybe where they are inside the atom orbitals. Quantum mechanical model actually helped us describe those orbitals better, which are electron probability maps that just show us the relative probability of finding an electron in various places surrounding the atom. Or the nucleus of the atom. And the electron configurations actually indicate which orbitals are occupied. Orbitals are filled in an order of increasing energy, and they obey the Pauli exclusion principle that each orbital can only hold a maximum of 2 electrons with opposite spins. And Hund's rule says that electrons occupying orbitals of identical energy actually go in singly before they pair up. The periodic table has elements with the same column, in the same column that have the same outer valence electron configuration, and therefore they have the same chemical properties. The periodic table is divided into blocks, S, P, D, and F, in which particular sublevels are filled. And as you move across the period to the right in the periodic table, atomic size decreases, ionization increases, and metallic character decreases. And as you move down a column, atomic size increases, ionization energy decreases, and metallic character increases. So hopefully these learning objectives here help you guys out. And of course, always ask questions in the discussion board. Keep up with the reading and do practice problems. Do as many as you can. In this case, the types of practice problems that I would look at just to solidify my understanding is maybe using the speed of light and some type of calculation to see how fast it would take to go somewhere. Knowing the order in which the light types of light are ordered by wavelength, frequency, and energy, meaning if I gave you 3 types of light, red light, ultraviolet light, and X-ray, could you put them in order of smallest to biggest wavelength or largest to smallest energy? Know about the Bohr atom. It would be nice if you guys could when we don't have the equations, I didn't give you guys energy equations, but read some of the practice problems relating to the Bohr orbit when it talks about electrons being moving from n equals 2 to n equals 4. Is that a being absorbed energy or is that releasing energy? Conceptually know what it means to say that an electron jumped to a higher level. Was a photon absorbed or was it released? That kind of stuff. If a photon, here's a good question. Photon A comes in and it raises electron 1 from n equals 2 to n equals 4. Photon B comes in and hits electron 2 and raises it from n equals 2 to n equals 3. Okay? The question might be something like that. Which photon, A or B, had a higher frequency? Or which wavelength was longer, A or B? Those kind of things. And you should be able to not spend too much time thinking about it to conceptually understand the difference. And I'll just kind of briefly state it here. Going from 2 to 4 requires a larger energy distance than going from 2 to 3. Larger energy corresponds with shorter wavelength. So so A had to have the shorter wavelength, the more energy, the higher frequency. B had the longer wavelength, the shorter, the smaller frequency, the smaller energy. All right, guys. As far as periodic trends go, electron configurations, writing electron configurations, you're going to have to practice those a little bit. Of course, use the periodic table for that. And if you have any questions, again, post them in the discussion board. All right, guys. See you next time.